Hello, my wonderful AP Chemers. Today we're going to start calculations with titrations, and we're going to start with strong acids and strong bases. So we are going to use HCl as our strong acid and NaOH as our strong base. We're going to use 10th molar of each, and we're going to start with our flask having some HCl. And we are going to put our NaOH in our burette and slowly add some NaOH to it and see what happens. So at the very beginning, we want to calculate the pH of just the acid that's in my flask before I add any NaOH. So here, I only have some HCl, and it's 10th molar HCl. So HCl is a strong acid. How do you find the pH of a strong acid? Well, you say my strong acid dissociates all the way, or ionizes all the way. If this was 10th molar, then that means this is 10th molar. And so my pH is equal to negative log of 0.1 molar, which is equal to 1. So that is my starting pH. Now, I'm going to go ahead and add some NaOH to it. So I'm going to open up my burette. Pretend that's my burette, and I'm going to add some NaOH in here. And I'm going to my 50 mils of HCl, I'm going to add 10 milliliters of the NaOH, and it just so happens that they're both 10th molar. So what do? Well, whenever you have a titration, you're adding an acid with a base together, they react. And so you want to write your reaction for that acid and base. So I'm going to go ahead and write that. Now, if you want to write it as HCl plus NaOH yields H2O and NaCl, by all means, you could do that. However, we know that NaCl, Na pluses and Cl minuses are spectator ions. NaCl does not contribute anything to the pH because it's neutral. And so if you have a strong acid, you can just write it as H+. And if you have a strong base, you can just write it as OH-. And so you can write it as just the net ionic H plus OH minus yields H2O. You can only do that with strong acids and bases. So only strong acids you can represent as H plus, only strong bases you can represent as OH minus. If it's a weak acid or a weak base, you got to write out the actual formula for it. Again, the reason for that is because your ions, the Na pluses and the Cl minuses, when you have strong acids or bases, their ions are going to be spectators and they're going to be neutral. They're not going to undergo hydrolysis or do anything at all. So you can do that with strong acids and bases. So what you do is write out your reaction. Acid plus base yields water. And we are going to write a BCA table for this. So sometimes we call it a BCA table for before, change, and after. Sometimes we call it our BCA table. R is for reaction. My students call it Rebecca, because it looks like Rebecca. And we usually do our BCA tables in moles. And so my stuffed mole is called Rebecca. So anyway, we are going to find the moles of each of our substances here. So let's start with the HCl. I have 50 mils of 10th molar, so 0.05 liters times 0.1 moles per liter. So this gives you 0.005 moles. So we're going to write that down, 0.005 moles. Let's look at our NaOH. In this case, I'm given 10 milliliters, and we know that it's 10th molar. So I'm going to do that on the side here. So 10 milliliters, 0.01 liters times 10th molar, which is 0.1 moles per liter. So this gives me 0.001 moles of my NaOH. Okay, I don't care really about water. Might change. So this is a reaction that goes to completion. When a reaction goes to completion, you basically use stoic, you use limiting reactants and all that. So you want to figure out which one is your limiting reactant. So in this case, you have 0.005 moles of this one, 0.001 moles of this one. It's a 1-to-1 ratio. So which one's your limiting reactant? Well, it looks like our hydroxide or our NaOH is our limiting reactant. So that means this is what gets used up. So we're going to use up 0.001 moles. So minus 0.001 moles. And same thing for this one, because it's a 1-to-1 ratio, we're also going to use 0.001 moles. So after the reaction is done, I don't have any more hydroxide, and I do have some HCl left over, 0.004 moles. When you're done with your Rebecca chart, you're going to get moles of what's left. You want to divide by the total volume. That way you get the molarity. So you can use that to find the pH. So my total volume, I have 50 mils of HCl and I have 10 mils of NaOH. So that's a total of 0.06 liters, which is 60 mils. And so that is 0.0667 molar. So now to find your pH, you look to see what kind of substance do you have left. So it looks like all we have left is just HCl. We have some water, but that doesn't really, affect anything. We don't have any more base. So all we have left is just HCl, which is a strong acid. How do you find the pH of a strong acid? Just do negative log of the concentration. So pH is equal to negative log of 0.0667. And so my pH ends up being 1.17. Okay, I want to show you visual for what's happening here. So I have some HCl. I have 15 milliliters of 10th molar HCl, which is equivalent to 0.005 moles, like we saw, like we just calculated. So I'm going to have each one of these HCl's as 0.001 moles. So since I have 0.005, I'm going to have 5 of them. Now HCl is a strong acid, so in water it completely ionizes, splits up into H pluses and Cl minuses, and so that means I'm going to have 5 of the H pluses and 5 of the Cl minuses separate. Just a disclaimer here, they don't line up next to each other like that. This is just so it's easier for us to see what's happening. And my burette is right now filled with NaOH. And so I'm going to dispense 10 milliliters of the 10th molar. And so that's equivalent to 0.001 moles. And so we said 0.001 moles is just one of the units, right? And so I'm just going to dispense 1 NaOH, right? So let's go ahead and do that. And so when I dispense my NaOH, the hydroxide portion of my NaOH reacts with H plus to form water. So I formed water here. And my Na plus, I form NaCl, but really NaCl is soluble, and so the ions split up anyways, they dissociate anyways. So they're not really they're just all swimming around, right? These are all just spectator ions just sitting there. So what do I have left in my flask? Well, I have some water and some Na pluses and Cl minuses, which are all neutral. And I also have some H pluses from my HCl. That's not neutral. So that's what's going to determine the pH, the H pluses that are left over. And so this is a strong acid, so you just take negative log of the concentration. Okay, let's look at adding some more NaOH. So now I'm going to add 50 milliliters of NaOH. So when I have an acid and a base in a titration, I'm going to write the equation for my reaction here. So again, same thing as we did before, we're going to do H plus OH minus yields water, 1 arrow. I'm going to write a BCA table. So my HCl is still 0.005 moles. I am now adding 50 mils of, excuse me, the NaOH. So let's figure out how many moles that is. So 0.05 liters, and we said it was 0.1 molar. And so that's 0.005 moles. So let's decide which one is our limiting reactant. They're both the same amount, and they're a 1-to-1 ratio. So that means there's no limiting reactant, right? Both of them will get used up. And so I'm going to use up 0.005 moles of this and 0.005 moles of this. So what am I left with? Basically just water, right? That's it. And some NaCl, which is neutral. When your acid and your base are both completely used up, you don't have a limiting reactant, this is your equivalence point. We are at the equivalence point. And because this is a strong acid, strong base, my pH is equal to 7. It is only equal to 7 at the equivalence point of a strong acid and a strong base. Why? Because what you're left with is just water. And again, NaCl in this case, which is neutral, and so your pH is 7. This is not the case if you're doing a strong acid, weak base, or a weak acid, strong base, or a weak, weak. So it's only a pH of 7 at the equivalence point if it's a strong acid and strong base. Let's look at our visual here for when we add 50 milliliters of my base. So I have 0.005 moles of each. So I have 5 of the HCl's, and then I'm going to release 5 of the NaOH's. So there's 1, 2, 3, 4, and 5. So again, the hydroxide portion will react with the H pluses to form water. And then I have my Cl minuses and my Na pluses. NaCl is a soluble salt, so they're just dissociating, they're just swimming around in the solution. So what am I left with? Water, Na pluses, and Cl minuses. All of them are neutral, and so the pH is equal to 7. Again, this only applies if it's a strong acid, strong base, because your salt that you're going to form with a strong acid, strong base would not undergo hydrolysis, it would be neutral. Okay, let's look at what if I add even more. So what if I've reached the equivalence point, but I just keep adding NaOH? So now let's look at 60 milliliters of NaOH. So again, I'm going to do the same thing. I have an acid and a base reacting together in a titration, so I'm going to write my equation for the reaction. 1 arrow. I'm going to do a BCA table, and my acid is still 0.005 moles. My base, I have 60 mils, so 0.06 liters times 0.1 moles per liter, so I get 0.006 moles. So now you look at which one's your limiting reactant. Well, it's a 1-to-1 ratio. This is 0.005, 0.006 looks like. My HCl now is my limiting reactant, so that's all going to get used up. So minus 0.005 moles. So this one's also going to be minus 0.005 moles. So at the end of your reaction, you have no HCl left, but you do have some hydroxide left. Let's divide by the total volume so we know the molarity, since this is just moles. I have 50 mils of the acid, 60 mils of the base, so 110 mils total, so 0.11 liters total. And so this is 0.0091 molar. So when you're done, you check out what type of substances are left. So we obviously have some water that doesn't affect the pH. We don't have any more HCl. We only have hydroxide, or sodium hydroxide, which is a strong base. So how do you find the pH of a strong base? You take the negative log of the hydroxide ion concentration, that gives you the pOH, and then subtract that from 14. So pOH is going to be negative log of the 0.0091. And so my pOH is 2.04. So my pH is 14 minus 2.04, which is 11.96. So at the equivalence point, or sorry, after the equivalence point, I've added more, and so my pH will go back up again. So let's look to see this as a visual here. So I have the 5 of the HCl's, and I'm going to add now 6 of the NaOH. So there's my 5, add some more, and so now it's left. So now I have my waters, which are neutral, my Na pluses and my Cl minuses, which are neutral, but I do have a hydroxide here that's left over, and so that hydroxide is what determines the pH. So because it's a strong base, do POH is negative log of the OH minus concentration, and that gives you the pH. Let's look at our titration curve here. So some things to look at here. This is my starting pH. So in this case, we calculated that to be a pH of 1. As I add my NaOH, my pH will start rising, and it will shoot up. The equivalence point, because this is a strong acid, strong base, is going to be at a pH of 7. That is when the moles of acid and the moles of base are equal to each other. That's when I reach my equivalence point. And again, it's only 7 when it's a strong, strong. If I keep adding more, it's going to keep going up. Like we saw at 60 mils, I'm at 11.96. And then it's going to start leveling off again. So what is the highest pH that it can reach? So imagine I just keep adding more NaOH and more NaOH and more NaOH. I add like gallons and gallons of NaOH. What is this value approaching? Well, at some point I'm going to add so much NaOH that anything else is negligible, right? So it's going to eventually approach the pH of just the NaOH. And so my NaOH in this case is 10th molar. And so that would be a pH of 13, right? And so the ending pH that it keeps approaching and approaching in my titration curve here, this is going to be equal to 13 in this case because my NaOH is 0.1 molar, so the highest pH that can reach would be the pH of that, so it would be 13. Next time, we are going to talk about weak acid and strong bases, and then strong bases and weak acids.